So let us talk about partial derivatives. So let's just review a little bit what we learned before. So these are partial derivatives. Why we are saying partial derivatives? Because here, instead of having one free variable, we have two free variables. First of all, recall that from your elementary calculus, if you have y equals to f of x, then you can find the rate of change of the function by taking the derivative of the function, and it has a limit definition. Then you use the shortcuts for some nicely defined function. The limit of f of x plus h minus f of x over h as h goes to 0. You have one free variable, but in this class, we are defining more free variables. We are defining a function, for example, in two free variables. Now, for a function like z equals to f of x and y, we are having two free variables. Two free variables. What's the meaning of that? It means that you can take the derivative with respect to x and also with respect to y. So we're going to call them partial derivatives. We take the derivative with respect to WRT or with respect to x, and we denote it by partial derivative of f with respect to x or f sub x. Well, it has a limit definition as usual. This guy is equal to the limit of f of x plus h and y minus f of x and y divided by h as h goes to 0. And we also have another free variable, y. We take the derivative with respect to variable y, and we write it as partial derivative of f with respect to y or f sub y, and the definition is the limit of f of x and y plus, for example, k minus f of x and y divided by k as k goes to 0. So these are the official definitions. Partial derivative of f with respect to x, partial derivative of f with respect to y. As you remember, if the limit exists, you can define those nice shortcuts. We have the same thing for multivariable functions. If this limit exists, if we are happy with the limit of these functions, then we can introduce the shortcuts as you saw before. So let us begin. If this limit exists, we work on the shortcuts instead. So let us go back to elementary calculus. For example, if you had f of x equals to x to power 3, the derivative of this function was equal to 3x squared, right? So if you had something like f of a times x, a is any number, any constant, ax, and it was defined, for example, as a x to power, for example, 2. Let's make it a little bit nicer. Or let's just write it simpler as ax squared. Ax squared. Again, a is just a constant. A is a numerical value. What's the derivative of this function? F prime of x. Let me just erase this and write it as f of x equals to, this guy becomes 2ax, right? So your a as a constant has no rule, has no part in taking the derivative of this function, right? Just copy this down to a x squared. For example, if you have f of t equals to, like, let's see. Let me give you something nice. A sine t, and if I ask you to find the derivative of this function with respect to t, f prime of t becomes a cosine t. Now, suppose I give you something like this. I say, hey, f of x and y is defined as 2x squared plus y. Okay, I have a function in x and y. I'm going to take the derivative with respect to x, and I'm going to take the derivative with respect to y. Since this is a nice function, we know the limit definition exists. When you're taking the derivative with respect to x, partial derivative of f with respect to x, y acts like a constant. Well, it means that we have 2x squared plus a constant. The derivative with respect to x is 4x plus the derivative of y acts like a constant, is 0. So partial derivative of f with respect to x is 4x. fx is 4x. The same when you're taking the derivative with respect to y. When you're taking the derivative with respect to y, x acts like a constant. X acts like a constant. Well, what's the meaning of that? It means that this term here is nothing but a constant. The derivative with respect to y, it doesn't have any y in it. It's going to be just 0. Plus, the derivative of y with respect to y is just 1. So, partial derivative with respect to y is 1.